as here, but there are some slight differences. Because you've got rotation, you can't expect things to be static. Static, of course, means that if you send t minus t, you get back to where you started from. If you have rotation, you don't get back to where you started from. The thing will be rotating in the other direction. So we want to call these things stationary rather than static. There is still a killing vector of time translation. And we'll call this k. But it won't be time-like everywhere outside the horizon. If you have something which is rotating, well, if you don't have it rotating, of course you get something which is spherical. There's a tendency to find, if you have rotation, that things get squashed. So the Earth is slightly squashed. It's bigger at the equator than it is at the poles. And that will cause deviations from spherical symmetry. These things are only axisymmetric. So there will be a killing vector associated with this symmetry. We'll call this MA. And I'll say a little bit about that in a moment. It means that the isometry group, instead of being SO3 times U1, I don't know why I called this U1, it should be R. The isometry group is going to be U1 for rotations times R. So you only have two killing vectors. The metric of the Kerr-Newman's family of solutions is quite complicated. It's not something that you need to remember, although the Kerr metric is of huge astrophysical importance. The important thing is to know that it exists and to know a little bit about its properties. So let's write down what it is, but I don't expect anyone to remember it, and I certainly can't remember it. I have to look at it every time I use it. So, the metric for the Kerr-Newman family in the kind of coordinates that we had before, t, r, theta, and phi, so that as r goes to infinity, the space-time looks like Minkowski space. The result is rather complicated. ds squared is equal to r squared plus a squared cos squared theta into dr squared over r squared minus 2mr plus a squared plus q squared plus d theta squared plus 1 over r squared plus a squared cos squared theta sine squared theta into a dt minus r squared plus a squared d phi all squared minus r squared minus 2mr plus a squared plus q squared into dt minus a sine squared theta d phi all squared, close bracket. So that's the line element. As you can see, it is quite complicated. The electromagnetic potential that comes with this is A T downstairs is equal to R Q times R over R squared plus A squared cos squared theta. But in any sensible gauge there's also an A phi term, and this is equal to minus AR sine squared theta divided by R squared plus A squared cos squared theta. So that's the sum total of that particular metric. M is the mass, a little bit more about that later. Q is the charge. And A is a rotation parameter. And I'll just leave it like that for the moment. This is referred to as the Kerr metric if Q equals 0. Otherwise known as the Kerr-Newman metric. As you can appreciate from just staring at this thing, it's rather an unpleasant object. Trying to do calculations in it is something of a nightmare. Therefore I won't do any. But what I will do is tell you what the differences are between Kerr-Newman and the Schwarzschild metric, so you have some understanding of what's really going on here. The first thing is that the situation is very similar in many ways to the Reissner-Nordstrom metric. This thing here, this quadratic polynomial, either has 2, 1, or 0 zeros for real r, and that divides this up into 3 different classes in exactly the same way as we had for the Reissner-Nordstrom metric. And in fact, the meaning is rather similar. The zeros are going to be at r is equal to m plus or minus the square root of m squared minus a squared minus q squared. And so you see that the criterion for these things is just whether or not m squared minus a squared q squared is positive, 0, or negative. Let's take the case where this thing is positive and there are 2 distinct zeros. Then you can immediately see that where there is a 0, this thing has got a coordinate singularity. That coordinate singularity is the horizon. You can get rid of these coordinate singularities. You can find out how to do this by looking in Hawking and Ellis as one possibility, or better still, the lecture notes of Brandon Carter in the Les Ouches proceedings of 1972. I won't go through the details of that algebra because it is too horrible, but I will draw the Penrose diagram that comes from this and explain what the differences are between the Reissner-Nordstrom spacetime and the Kerr metric. Just as before, there is an asymptotically flat region that represents something that we expect to live in. There is an inner region here and then a further region out here. So this is, surface will be at r is equal to m plus the square root of m squared minus a squared minus q squared. This surface here will be at r is m minus the square root of m squared minus a squared minus q squared. This thing is sometimes called the inner horizon, And this one is usually called the horizon. And then the pattern is very similar, except that this region is a little bit different. So out here, you're going to have another asymptotically flat region. Here you have another inner region. Here you have another region like that. And this picture goes on forever in both directions. In the case of the Reissner-Nordstrom solution, this region here contained a singularity and was bounded by a singularity. In the case of the Kerr metric, it's a little bit different. There is a singularity which sits here, which I'm going to draw like this. The reason that I've drawn it like this is that if you calculate the curvature tensor, I'm going to calculate RABCD, RABCD. You will end up with 48m squared over r squared plus a squared cos squared theta cubed. I don't advise trying this calculation. But you can see that the curvature only blows up if r equals 0 and cos theta equals 0. So that tells you that theta is equal to pi by 2. That tells you that the singularity only exists in the equatorial plane of the theta phi coordinates. So in actual fact, you'll discover that the singularity is in fact just sitting in part of the space. It doesn't completely block the space off. If you compute the proper radius of the singularity, you'll discover so what you'd have to do is to calculate its proper radius from the metric that I gave. So it would be for constant t, r, and theta equals pi by 2. So it's described by phi. You'll discover that it has proper radius 2 pi a. In other words, the singularity is a ring sitting in the equatorial plane. So if you wanted to draw it, you could draw it in, so fix t and, we'll just fix t, I think. So let phi be going round in that direction. The singularity just looks like a ring sitting in space. That, of course, means that you can go through the middle of it. And unlike what happens in spherical polar coordinates or the Reissner-Nordstrom or Schwarzschild solutions, r can become negative. That's why I've drawn this region out here. This region out here where r is negative, well, we looked at the curvature, we discovered that Riemann squared looked like 1 over r squared plus a squared cos squared theta cubed. So if r is negative and large, this thing is going to 0, and so this is another asymptotically flat region. So that's a significant difference from what happens in the Reissner-Nordstrom metric. And then, of course, this pattern just repeats everywhere, down that direction forever and up that direction forever. Yes? Sorry, start again. Yes? Oh, what happens to a light ray? Well, so if you want to draw null lines on this picture, if you're sitting here in a region outside the black hole, then of course light rays can go out like that, or they could fall into the black hole, in which case they'll go in like this. If they're in the equatorial plane, they will meet the singularity, whereas if they're not in the equatorial plane, they can just keep going. So it could look something like that. The question might be asking, do all light rays do that? And the answer is no. Some of them will spiral around the black hole. The path here is sort of an idealized radial path. The question that you're really asking is about what are all of the geodesics in the Kerr metric. That is an amazingly complicated question. It has been simulated on a computer. If you watch the movie Interstellar, which, despite the fact that a lot of it is complete nonsense, he went to great lengths to simulate the correct geodesics in the Kerr metric, and so the images that you see there actually are a fair representation of what actually happens. For the Kerr metric, it is really only possible to simulate those on a computer, if you want all of them. Even for the Schwarzschild metric, if you want to find all of the geodesics, it involves elliptic functions if you try to do it in closed form, and for the Kerr metric it is a worse mess. I wasn't planning on doing this, but you can do things for Schwarzschild, analytically calculate things like cross sections. Fairly easily. I'm not sure that I really wanted to do that because there are other things that we should be doing. There are many references on the subject. I guess I can find a good collection of them for you if you want. It's really only important if you want to do astrophysical calculations. I think most of the physics calculations, you don't need to worry too much about this. Or at least I never have had to. There is another problem with the Kerr metric that is not found in the Schwarzschild metric or the Reissner-Nordstrom metric, and that is an issue close to the singularity. If you look at the coefficient of d phi squared, close to the singularity, you'll discover it is negative. That's very unfortunate. That means that if you fix t r theta, then phi goes to phi plus 2 pi. Remember, that takes you back to the same point that you started from. So in other words, this is a closed loop. Between the same points in space time. The physical significance is this because d phi squared has got a negative coefficient. This curve is time-like. That means that close to the singularity, somewhere in here, there will be a region in which there is causality violation. Moving along a closed time-like path between the same point in space-time leads to all kinds of paradoxes. So if you drew a little picture of the ring singularity, so here is the singularity, what you'll discover is that inside it, in a donut-shaped region around it, on the inside, so it looks something like this, is the region of causality violation. I can't really draw a donut easily, but I hope you get the idea. The singularity is this white region. Just like the Reissner-Nordstrom solution, the way in which you rescue yourself from these kinds of paradoxes is presumed to be the following. We should say that perhaps this is unphysical. Because the inner horizon is unstable. The precise meaning of that is not yet known. So those are some differences between Reissner-Nordstrom and Schwarzschild. Because they're inside the horizon, perhaps we don't care too much. But there is something which happens outside the horizon which makes Kerr black holes dramatically different to the Reissner-Nordstrom and Schwarzschild metrics. Let's look again at this killing vector Ka. So that one way of looking at it is to say that it's got components 1, 0, 0, 0. If you ask yourself about a particle, it will in general have some kind of velocity 4 vector UA, and its energy is going to be UA Ka with a minus sign with my conventions. However, Ka outside the horizon is not necessarily time-like. It can be space-like. So this thing is space-like inside a region known as the ergo region. And in the ergo region, you can have E negative. But still, the particle will move along a time-like trajectory. Where is the ergo region? Well, if we look at the coefficient of dt squared, we will discover it's equal to, and that controls whether or not k is space-like, time-like, or null. This is equal to 1 minus 2m minus r minus q squared over r squared plus a squared cos squared theta. And this thing will be negative inside, this is minus the coefficient of dt squared, inside the ergo region. Let's draw a picture of what that is. Let's suppose that we have let's draw a picture of fixed t and phi. The thing is axisymmetric, so I can just simply take a section through the thing. And let's suppose that the horizon is here. So that phi would go round in this direction, and so the black hole will be rotating about this axis. So here is the equator. Then the ergo region is a region which intersects the horizon at the poles, but is the interior of this orange region. So this shaded area is the ergo region. Another thing that you can do is to draw a picture of the equatorial plane to see what this actually means. So in the equatorial plane, so in other words, it's going to be a section through something like that. We have the horizon sitting here, and the boundary of the ergo region sitting here. Now, suppose, for example, that I'm sitting a long way away from the black hole, and I consider a point in space-time here, and I release a little burst of light. What will happen is that it will spread out in a spherically symmetric way. Of course, I've only drawn this through the equatorial plane. It will spread out a little bit like that. When you get to the surface of the ergo region, then essentially this shell of light is dragged around by the rotation of the black hole, so that instead of looking like this, it will look something like that on the ergo region. If you release a flash of light inside the ergo region, then it will be completely removed from that point, something like that. On the ergo region itself, this thing will always touch at this point. So that's usually sometimes referred to as frame dragging. And is partially responsible for the huge distortions that you will see in the neighborhood of a Kerr black hole. Last, but I'm not going to demonstrate this in any length, because you can have negative energy states inside the ergo region, you can use that to mine energy from the black hole. These can be exploited to extract energy from the system. This is so-called Penrose process. To explore the details of Penrose process, you have to look at the behavior of particles in the vicinity of the black hole, and it is a little unfortunate that I don't think we have got time to do that. So that's what happens when you have a black hole space-time. What about these other two cases? Well, they're basically very similar. I don't think we need to look at those in huge detail. So case B, if m squared is equal to a squared plus q squared, then the horizon generates and these intermediate regions get squeezed out of existence, but otherwise it's similar. That's really all you need to worry about. Case C, m squared is less than a squared plus q squared. That corresponds to a naked singularity, but in this case it will be a ring singularity. It'll come with its causality violating region, and you can go through the middle of it and find yourself in the same asymptotically flat region. This is just a horrible space-time. I don't think it's a place someone would want to live. Yes? In case B, the ergo region is similar to the case that we had in case A. In case C, let me think about this for a minute. Case C is not usually something that I want to think about. There is an ergo region for R sufficiently small, in case C. But there are so many other problems with this space-time that I don't think that we should worry too much about it. So those are all properties of black hole spacetimes. Well, we've had a list of black hole spacetimes and we've been studying them. These are all static or stationary and asymptotically flat. It looks like there's a list like this that could go on forever. Yes? I'm going to talk about that probably in the next lecture. There's a general way of describing these in terms of the Noether charges, but this is not the time to do it. So the real question is whether or not this exhausts all possible equilibrium states of black holes. And the answer is that if you are asymptotically flat, this is essentially all there is that is stationary. You might think that by including various kinds of matter, you could get around this. And the answer is that you can't. There are some small exceptions to this statement, but they won't change anything that we're really thinking about at the moment. This statement usually goes by the name of the no-hair theorems. The term was introduced by John Wheeler way back in the 1960s, and the analogy is simply that if you see someone who is bald, you can't tell the difference between that person and any other person. Well, we all know that's not true, but it's a good story. So how do you prove the no-hair theorems? Yes? Soliton, you say?
The notion of horizon.
Oh, horizon.
You survive to the absence of timeline Killing vectors. Is there any exact result about this point?
Well, the Killing vectors are not time-like everywhere. So I understand. I understand the problem now. The answer is that a horizon does not require you to have a Killing vector. These exact solutions of the Einstein equations do have Killing vectors, and the fact that they've got Killing vectors makes them easy to see. The question is really about time-dependent spacetimes, and there is nothing stopping you having a horizon in a time-dependent spacetime. And indeed, I think probably, with a bit of luck today, we'll see an example. The reason that I wanted to look at an example whether there was evolution is because ultimately we'll be interested in how black holes form from something that is perfectly normal. All of these examples that we've had so far are unphysical in the sense that although they're stationary, so in the future you'd expect these to be the things that black holes evolve into, they all have in their past white hole horizons, the time inverse of black hole horizons, and singularities in the past. And that somehow stops them being physically what you actually want to explore. So what I was going to do soon was to look at an example of gravitational collapse where you do have time dependence forming a horizon. So the answer is that you do not require a killing vector to have a horizon. The two are entirely different concepts. Remember that a horizon is defined to be the boundary of the causal past of scry, and that doesn't require you to have a killing vector. So a proof of all of the no-hair theorems is quite complicated, so what I'm going to do is to prove about the simplest no-hair theorem that you can think of and show you that all the other ones are basically variants of this. So I want to imagine a static, spherically symmetric space-time. No, I don't want to do that. I just want to imagine a static space-time that is asymptotically flat. And I'm going to consider the Einstein equations coupled to a massive scalar field. So the kind of picture that I'm contemplating is essentially like the Schwarzschild metric. And I'm only interested in what happens outside the horizon. So the Penrose diagram is imagined to look something like this. And I don't care what happens beyond here. So this is the horizon. Here is scry plus and scry minus, and I0 and I plus and I minus. And I'm going to imagine that I've got some kind of non-vanishing scalar field in the middle, phi. This phi is going to obey the Klein-Gordon equation, which is box minus m squared acting on phi equals 0. So let's contemplate what this static metric is going to look like. There will be some function of position dt squared plus something space-like. There will be no GTXI terms because we have asked the space-time to be static. So the time-like direction is entirely here, and this is entirely space-like. That means that gamma ij is a positive definite matrix. At infinity, v is going to be tending to 1 minus plus 1. On the horizon, v will be tending to 0. So now what I want to do is just to take the Klein-Gordon equation and show that you can have no solutions which are independent of t. So what you do is you just simply integrate the Klein-Gordon equation over the space-time. This is equal to 0. But if you integrate it by parts, Because there is no term which depends on time, this thing becomes minus gamma ij di phi dj phi minus m squared phi squared square root of minus g d4x minus the integral of something over the boundary. And the thing on the boundary is phi gab db phi, what it is, nb, that's why I call this a, nb ds, where this thing is the unit normal to the boundary. So if you can show that this term is 0, since this term has definite sign, phi and grad phi must be 0 everywhere. At infinity, it's easy to work out the behavior of phi. It must be exponentially damped, e to the minus mr times some function of position. So that's not going to give you any contribution. On the horizon, all you know is that n is null. So the way to deal with this is just to define a vector v to be equal to phi dA phi. Then what this thing here is basically VA NB GAB. However, that thing is a bit of a mess, but the Cauchy-Schwarz inequality tells you that the square of this must be less than or equal to VA VB GAB modulus NC ND GCD from Cauchy-Schwarz. But on the boundary, which is the horizon, this thing is n is null, so this is 0. So this thing must be 0. So there is no contribution from this boundary term. You know that this thing is equal to 0, and that tells you that phi is 0 everywhere. So that shows you that a static black hole cannot act as a source of a massive scalar field. So that was relatively simple. Other uniqueness theorems, other no-hair theorems, are rather more complicated. There is a small corollary to this, and that is what happens if m squared is equal to 0. If m squared was equal to 0, what we've shown is that the integral of gamma ij di phi dj phi is equal to 0, and nothing else. So that would allow you to have phi equals constant. That's a sort of boring solution, and besides which there are no master scalar fields known to mankind. So this is a possible way out, and indeed it does tell you something that is worth bearing in mind for what will come later. All other no-hair theorems work in a similar way, but as I say, they're vastly more complicated. The next thing I want to think about is a very classic theorem known as Birkhoff's theorem. This is a very simple theorem to state. It just simply says that if you have, let me get it the right way around. It says that if you have a vacuum space-time that is spherically symmetric, it's static. And hence Schwarzschild. How do you prove that? Well, this is quite simple. I'm not going to go through the details of it, but let me just quickly sketch how you actually do this. Simply because the method is really quite simple. So let's just write down what you'd expect from a spherically symmetric space-time that is not static. You'd end up with something which looks like minus v, which is a function of r and t, dt squared, plus w, that's another function of r and t, dr squared, plus r squared into d theta squared plus sine squared theta d phi squared. Now what you need to do is to calculate what the Ricci tensor is. And then put it equal to 0. So I think the thing to do to start with is just to write down one component of the Ricci tensor, and that's RTR. This thing has got to be 0, but if you take the line element that we've got here, you'll discover it's equal to W dot dW dt divided by WR. So that immediately tells you if it's 0, W dot is equal to 0. So at this point you're halfway there. The next thing to do is to calculate some other components of the Ricci tensor. So let me tell you what to calculate. The thing to do is to calculate WRTT plus VRRR. This must be equal to 0 because these things are supposed to be equal to 0. If you do that, I'll leave these things as homework for you. You'll discover that W prime over W plus V prime over V is equal to 0. This is independent of t, so this must be independent of t. And this tells you that W is equal to some constant divided by V. And if you want the thing to be asymptotically flat, V and W must go to 1 at infinity. So that really is the end of the theorem. That will then tell you that the thing has got to be the Schwarzschild metric. You should have suspected that. How could a spherically symmetric spacetime be anything other than static? Well, if you just have something which is spherically symmetric on its own, and there is no other matter field present, then it clearly can't do anything, for the very simple reason, except expand or contract, for the very simple reason that the only way it could do anything would be to radiate gravitational waves. There's nothing else it could do, being a vacuum space-time. But the only way a vacuum space-time can radiate gravitational waves is if it has a time-dependent quadrupole moment. Being spherically symmetric, it can't have a quadrupole moment, time-dependent or not, and therefore there's nothing it can do. So it's hardly surprising that we found a static space-time as a result of spherical symmetry. You can go a little bit further with that idea. The Kerr metric is an example of a space-time which is almost static, it's stationary. It represents a black hole that is rotating and it's squashed. But that corresponds to a deformation that only is basically a dipole deformation, has L equals 1. It does not have a quadrupole moment, and therefore even though it's a time-dependent solution to the field equations, it has no time-dependent quadrupole moment, and it also won't radiate. So that tells you, roughly speaking, that you should only expect a space-time to evolve if it's got time-dependent moments that are higher than dipoles. So that's a sort of physical explanation of what Birkhoff theorem and its descendants is about. We will appeal to the Birkhoff theorem very shortly. Now, all the examples we have seen so far are just of black hole spacetimes that sit there. Something has happened to give rise to a black hole spacetime, but the real question is what and how do you actually form a black hole? So the first thing to do would be to convince ourselves that somehow there is a necessity for something to go wrong with the idea that a star could be infinitely massive. In other words, why there should be gravitational collapse to form a black hole in the first place. So what is the argument? There's a very simple argument, originally due to a clergyman called John Michel. Of course, he was a Cambridge graduate in 1784. He just simply said, well, suppose you had an object of mass m, radius r, he was an adherent of Newton's corpuscular theory of light, and therefore he asked what happens if a light ray leaves this object in that direction, upwards, will it always escape? And of course the answer is no. If its velocity is less than the escape velocity, it won't reach infinity. He computed the escape velocity and concluded that if 2gm over c squared r was less than 1, c being the velocity of light, then it could not escape. That's the same as the condition that you get from the Schwarzschild metric. So he was, roughly speaking, 132 years ahead of his time. There is a similar result due to Laplace in 1798. But the question you want to ask is this condition ever realizable for an honest star, or body of any kind for that matter? So that's the question that we want to actually address now. Can you have static objects in relativity of arbitrarily large mass, or does something go wrong? So let's try to build ourselves a star, or something like that. What will happen? Well, let's construct a star first of all. So a star is something which is, we'll take a spherically symmetric one because anything else is going to be too complicated. Let's suppose it has got mass m. Its surface is at R. Outside the star, what we have discovered is that the metric must be the Schwarzschild metric. That's an application of Birkhoff's theorem. So we can just simply write down what that metric is. We all know it by now, I hope. What happens inside the star? Well, that's a bit more complicated, but we just need to think of some spherically symmetric metric. So this is for r greater than r. For r less than r, we're going to assume that the metric is just simply of this form, minus e to the plus 2 phi, which is some function of r times dt squared, plus 1 minus 2. Well, this is going to be some general sum function of r, but because people have done this calculation before, I'm going to write this in the form m of r divided by r. Of course, any function of r can be written in that way, but this was a particularly inspired guess. And of course, you need the metrics to match up. So that tells you that m of big R is equal to big M. And it tells you that e to the 2 phi of big R is equal to 1 minus 2 big M over R. Now what you need to do is to determine this function little m of R and big phi of R. To do that, you need to know something about the energy momentum tensor of the stuff that makes up the star. The energy momentum tensor, TAB, We can take it to be that of a fluid with for velocity UA. And then you'll discover that the remaining components of the engine momentum tensor are P plus rho UA UB plus P times GAB, where P is the pressure in the fluid and rho is the energy density. So what we need to do is to find a solution of the Einstein equations where P and rho and U are only functions of R. They don't depend on time, where the space-time has this particular form. So let's do this calculation. The first thing is to look at the velocity field UA. UA is equal to -1, because velocities are always normalized that way. And so that tells you UA with its index upstairs is equal to e to the minus phi. Yes. 0, 0, 0. And UA with its index downstairs is e to the plus phi. 0, 0, 0, and a minus sign. So that's the form of the velocity. Then the simple way to proceed is to just write out the conservation law for the energy momentum tensor. Del A of TAB is equal to 0. If you just substitute in TAB from the far left here, you'll discover that UA del A of P plus rho times UB plus P plus rho del A UA times UB plus P plus rho UA del A UB plus del B of P equals 0. So that's just the conservation law. However, everything is independent of time. UA only has a time component, so this is just d by dt, so this term gives me nothing. Similarly, this term might give me something, this term might give me something, and del B of P might give me something. Let's think a bit harder about these terms. I want to keep this, so let's get rid of this. Let's write out the terms that are left. So let's start with this one. This is P plus rho 1 over the square root of det G partial A plus the square root of det G UA times UB plus P plus rho UA into del A UB minus gamma ABC UC plus del B of P. That's equal to 0. We can now get rid of this term. The only component of U that doesn't vanish is the time component. Nothing depends on time, so this term goes away. So we're left with one simple equation, namely that P plus rho let's not write it that way. But dB of P minus P plus rho. Let's look at this thing. The only interesting components are 0 and 0, so there will be a 0, U0 upstairs, gamma 0, 0, B, U0 equals 0. The only interesting component here is the R component. You can see this by just working out what the Christoffel symbols are. 0, 0, R, and gamma 0, 0, R is just d phi dr. So we have a nice looking equation for the pressure. I still want to keep this thing here, so I'm going to get rid of this. It reads dP dr plus P plus rho d phi dr is equal to 0. So this is really the relativistic version of the thing that says that pressure is minus the gradient of the gravitational potential. Phi, you see, is like the Newtonian potential. So this really reads grad phi, and this really says that pressure is minus grad phi times the energy density. Notice there is a pressure term sitting in there. The remaining equations are a bit more difficult. You have to get these from the Einstein equations. The 0, 0 component of the Einstein equations is fairly easy. Well, they're both fairly easy to work out, but it's a bore. I mean, it's not something you want to do. The 0, 0 component gives you 2 over r squared dm of r by dr is equal to 8 pi times rho, and the rr component gives 2 over r into 1 minus 2m over r d phi dr minus 2m over r squared is equal to 8 pi p. The 0, 0 equation is easy to understand. It's just the usual formula for the mass inside some region bounded by radius r. It basically says that m of r is the integral from 0 to r dr prime 4 pi density r squared. So in other words, the mass function is what you thought it was. That's what motivated this choice of the metric coefficient here. This equation here, well, that's just horrid, but roughly speaking, that's the relativistic analog of Poisson's equation. The only thing I have covered up here is an integration constant, but I just took m of 0 to be equal to 0. In other words, there's no delta function at the origin. What you can do is to substitute this thing into here to get rid of d phi dr, and you will end up with dp dr is equal to minus p plus rho over r into r minus 2m of r into m plus 4 pi r cubed p. This last equation is sometimes referred to as the Oppenheimer-Volkoff equation. Because, as far as I know, they were the first people to write down this particular thing. Lastly, there's some boundary conditions that apply to the star. The surface of the star is defined by where the pressure is equal to 0. So P of capital R is going to be equal to 0. And that's the boundary condition that we have got. Well, that's as far as you can go without making some kind of specialization. The problem is that in ordinary matter, there is a relationship between the pressure and the energy density. Sometimes called the equation of state. For realistic equations of state, the only way which you're going to get anywhere with these equations is to integrate them numerically. But there are some nice limiting cases that you can do analytically, and the result is pretty much the same whatever you do. So we'll do the analytic case because it's something that you can actually manage to do. So the analytic case simply corresponds to incompressible fluid, something like water. It's not brilliantly realistic, but as I say, if you do something more complicated, you have to do it numerically, and it doesn't make a great deal of difference. So let's look at incompressible fluids. These are such that rho is a constant independently of where you are. Let's call this 0. What then happens? Well, the first thing that happens is that you can work out m of r exactly. M of r is just equal to 4/3 pi r cubed rho naught. That tells you immediately that the total mass of the star, capital M, is equal to 4 pi over 3 rho naught big R cubed. Now you can substitute back in and find the pressure and the gravitational potential as a function of R. Let's do that. Uh, Doing the integrals is a little bit tricky. You can go home and check this if you like. That must be cubed. So that's pressure as a function of R. If you calculate e to the phi, you will discover for R less than R, it's equal to 3/2 of 1 minus 2m over R to the half, minus a half into 1 minus 2m R squared over R cubed to the 1/2. And of course, for greater than R, it's equal to 1 minus 2m over R to the half. So that's the solution to those equations. Do you notice anything strange about this? Well, I hope the answer is yes. You can look at the pressure at the center of the star. P of 0, that's equal to rho 0 into. This gives me a 0. I end up with a minus 1 minus 2m over R divided by 3 minus 1 minus 2m into 1 minus 2m over R to the 1/2 minus 1. You will notice that something bad happens if this thing is equal to 0. 3 into 1 minus 2m over R. Missing a 1 on top. That's better. So this would imply the pressure is infinite. Is that possible? Plainly not. So there's a physical limitation on how big a star can be at fixed size. Let's work out what that's going to be. Well, it's kind of easy. You just square this whole thing, and we're done. 9 minus 18m over R equals 1. So in other words, 18m over R is equal to 8 or alternatively r must be bigger than 9m over 4. In other words, slightly bigger than its Schwarzschild radius. What is the lesson from this? Well, if you had a star of some fixed size and you try to put more stuff on it, something will go wrong. The pressure will become infinite, and plainly this approach isn't going to work. It's worthwhile putting in some numbers so that we can see exactly what's happening here. Numbers are always good. So, I'm going to pick a density of 5 times 10 to the 14 grams per cc. You might ask, why did I pick that density? The answer is that this is, roughly speaking, the density of the nucleus. In other words, it's what I imagine a neutron star to be. What is the size of a neutron star? Experimentally, you can go off, well, I say experimentally, observationally you can go off and measure it. Best measured by, well, I'm not quite sure exactly what the best way of measuring it is. 15 kilometers. What is the maximum mass? Is equal to 3 solar masses, if you do that. So that tells you the sort of scale of things that are involved. It tells you something about the nature of neutron stars. You can't have neutron stars with a mass bigger than around 3. What will happen? Well, the way in which you get round this is to try to ask yourself what dynamical process is going to occur if the mass is too big. Well, the answer is kind of obvious. Since gravitation is attractive, there will be further gravitational collapse beyond the neutron star stage. So let's see if we can model gravitational collapse. There are some problems with modeling gravitational collapse, and that's simply that, again, the nature of the equation of state turns out to be important. So I'm going to do a very special equation of state, which is just pressure-free matter. It's a simple model. Again, if you change this, you have to do it numerically, but it does show you more or less what's going on. So this basically follows a treatment of Tolman, which is kind of old. I'm going to have pressure-free matter, meaning that P is equal to 0. The energy momentum tensor is then equal to rho UA UB. And if you just work out the conservation law, you will get that UB del A of rho UA. So that's where I take the divergence of those two plus rho UA del A of UB is equal to 0. So that's where I took those two to take in there, and then I differentiated that one and got that. The equation of continuity, conservation of mass, tells you that this term is 0. This term, however, now becomes nice. It's just a geodesic equation. So now we're in a position where we can actually go and do a calculation. So the calculation that I want to do is the following. The initial condition is going to be a ball of stuff, spherically symmetric, of constant density at rest. Spherically symmetric, constant density at rest. And I just let it go and ask what happens. The problem is very similar to the problem we had before. There will be some metric outside the space, outside this ball, and it'll be something. Let's suppose that the ball has got mass m. What is the metric? Well, the answer is a Schwarzschild metric as a consequence of Birkhoff's theorem. So outside, ds squared is equal to minus into 1 minus 2m over r dt squared plus 1 minus 2m over r to the minus 1 dr squared plus r squared d omega 2 squared. I'm going to call this function here v of r. Now what happens? Let's look at a particle sitting on the surface of this ball. What will it do? Well, the thing is gravitating, so it attracts things in, but it will follow a geodesic because there's this, and the metric outside and on the surface of the ball is precisely the Schwarzschild metric. So all you have to do is to look at what happens in the Schwarzschild metric to figure out how this particle moves. So UA is going to be equal to, well, let's see. The easiest way to do this is to introduce some kind of parameter, affine parameter, which I think I took to be equal to eta. And then ut is just t dot, ur is r dot, and I just substitute into the geodesic equation, and I will discover that r dot and t dot are given by the following nice relations: minus e over v, and this one will be equal to minus v plus e squared to the half. If you have done any analysis of the motion of a particle in the Schwarzschild metric, this will seem familiar to you. You can integrate these things up. It's horrible. Let me tell you the answers. Let's start off at r equals r. You will discover that little r is equal to a half big R into 1 plus cos eta. You will discover that t is 2m times the logarithm of r over 2m minus 1 to the half plus tan a half eta divided by r minus 2m minus 1 to the 1 half minus tan a half eta plus 2m r minus 2 over 2m minus 1 to the 1 half times eta plus r over 4m into eta plus sine eta. And if you're interested in proper time on the particle, this is equal to r cubed over 8m to the 1 half times eta plus sine eta. And this thing should not be eta, but it should be tau, I beg your pardon, proper time. So those are the integrals of the geodesic equation. Probably this one doesn't matter too much. The one that's important is this thing. It tells you what has happened to the surface of this collapsing body as a function of time. So the proper time is given by this thing, and the r is given by that thing. So you can see as eta tends to pi, r tends to 0. So what has happened is the following. At eta equals 0, t equals 0, and the thing is just sitting there like that. As eta increases, then the thing has shrunk, and when eta is equal to pi, in these coordinates, the thing has shrunk to a point, because r has gone to 0. The value of tau is easy to work out. Sine pi is 0. This thing gives me a pi. So tau is equal to r cubed over 8m to the 1 half times pi. So what that tells you is that the thing has shrunk to a point in finite proper time. Furthermore, the size is this as a function of proper time, here written parametrically in terms of this quantity eta. Well, that's fine. That tells you what's happened to the ball as far as the outside of the space-time is concerned. What's happening in here? And what's happened when it's collapsed down to a point? So the question is, what is the space-time inside? I think that's a good place to stop for today. I'd like you to contemplate what the space-time inside the sphere is, and the hint is to look at this formula and this formula. Forget about this one, this is too complicated to even imagine thinking about. But these two things give you a clue as to what the interior of the space-time actually is. So let's stop there.